Hi, welcome back. So we've been talking about temperature, and we've looked at thermal expansion, and now I would like to go to the concept of an ideal gas and see how it is affected by a change in temperature and how that's going to relate to other properties of the gas. So even though, so we've talked about liquids and gases when we talked about fluids before, and in this particular part of the chapter, we're going to talk specifically about an ideal gas. So the first thing to do is to actually define what an ideal gas is going to be. So, and also why we're spending this time particularly on these ideal gases. Um, as we just saw for when we talked about thermal expansion, if you consider a solid or a liquid quantity, for a given temperature, you're going to have a given value of the volume. All right. So in most cases, as the temperature rises, so will the volume. Okay. For gases, things are a little bit different because the volume is going to be determined by the container. So just imagine that you have a closed box with some air in it or some gas, and basically the volume is going to be the size of the container. If you had a liquid in that container, things would be different, right? So it would take up, if you put some water in a beaker and you change the temperature, you may see a change in its volume. It's not taking up the whole container. For a gas, it's going to be different because it's taking up the entire space of that container. And things are different with gases because gases are held by, so if you look at the molecular level, you have the forces that keep everything together, those interatomic forces inside of your gas, keeping it, making it up, your gas, they're very, very weak, these forces. Um, so we will assume that the volume of the gas is going to be given by the volume of the container. So as long as you don't change the size of a container, you're going to keep a constant volume. Uh, and in that sense, we have to talk about this situation in particular because it's different from what we've seen for solids or liquids. So what applied to solids and liquids is not going to work here. So what do we do when we are looking at gases? We're going to actually make an approximation and look at ideal gases because they're easier to describe. And so what is an ideal gas? An ideal gas is a gas that is going to have low pressure, low density, and far from condensing. So what does it mean? It means that if you look again at the molecular level, we're going to assume that there's no interactions between the molecules. So you can think of your box as filled with molecules of your gas, but they are not interacting with each other. So they're always almost like you could consider a bunch of dots that are independent from each other. Okay, and so there's no attraction or repelling effects within your container. So now, based on this idea, so just you can picture that you have your gas and you can see a number of little particles that are independent from each other. And so there's a couple of things that were observed, which were the fact that if you keep your container the same, so you don't change the volume, so we keep the volume constant, then if you raise the temperature of the gas, you see a change in the pressure. So as the temperature increases, so does the pressure. Okay. And I'll show you an animation that, or a simulation that shows you this. In some ways, this makes sense because if the temperature is increasing, that means that your molecules are moving faster within the container, and that's going to make it so that you have more collisions with the walls, and that's going to increase the pressure. Okay. Now, if you're able to keep the volume constant, so again, you keep the same container, you don't change the volume of your container, and now you keep your temperature constant. However, you add more gas inside, so you put some more gas in it. What you find again is an increase in the pressure of your gas, which also kind of makes sense if you think about it in terms of what that would feel from the perspective of the container, the walls of your container. Then with more molecules, you're going to have more collisions with the wall, you're going to have increased pressure. Now, if you keep the temperature constant, but you change the volume, that also affects the pressure. So let's say you have an open container, but you close it with something with a piston, so you can change the top, right? And so let's say you're now pushing down on the top. What that's going to do is also increase the pressure. Okay, you could also have it where so if I added mass to the top, right, and it brought it down, if I remove the mass, then the my gas would actually work on the top and expand. So and that would decrease the pressure that we would measure inside. So we can put all of these observations together in what we call an equation of state, because an equation of state is described by these quantities that are going to show up here. So P is the pressure, N is going to be our number of molecules, T is going to be the temperature, and V the volume. So a given state of our gas is going to be described by given values of pressure, number of molecules, temperature, and volume. K here is a constant. And so this is the equation of state for an ideal gas. So it can be arranged in different ways depending on what exactly you're trying to calculate. Most of the time you'll see it written in the form that is seen down here. So PV equals NKT. So again, K is a constant, which is called the Boltzmann constant, which is equal to this. You can see it's an extremely small number, 1.38 times 10 to the negative 23 joules per Kelvin. I would like to see you to notice the units here. So you can see this is given in joules per Kelvin. So we're going to assume a temperature in kelvins and everything else in SI units. So we're going to use a pressure in pascals and a volume in cubic meters. Okay. So just be careful with your units. All right. So again, just noticing that this is given in kelvins. All right, so make sure that your temperature is also in kelvins. All right, and so you can see that if we go back to all of the observations that we made, all right, if we look at this, the pressure will increase if the temperature increases with everything else held constant, so volume constant. The pressure will also increase if we increase n the number of molecules and we keep everything else constant. And you can see that the pressure will decrease, however, if everything is constant except for the volume. So if we increase the volume, the pressure is going to decrease. Okay, so the pressure is inversely proportional to the volume and directly proportional to the temperature, for example. So this is in some ways something that is simple because it's one equation that relates all of these quantities. And it's very, very powerful because that means that if I have enough information, let's say about temperature and volume, I may have enough information to figure out the pressure of my gas. Okay, so let's take a look at an example and apply this. So we said PV equals NKT, all right? And so usually I do this in the classroom, but you could look at the measurements of the room that you're in. So let's say we have a room, we measure the dimensions. It's a nice kind of simple, like a box, so 4 by 5 by 6 meters, sorry. we want to find the number of molecules that we have in this room, given that it is at a temperature of 20 degrees Celsius and that the pressure in the room is the atmospheric pressure of 101 kilopascals. So if you want to do this on your own, please pause and come back to us with, as I'm working through the solution next. Um, so we just say that PV, so pressure times volume, is equal to N KT. All right, so in this particular case, we're going to be solving for N. We're given the temperature, okay, 20. But you can see that this is something that is given in degrees Celsius. So the first thing I'm going to do is convert that to Kelvin. So 200. So to convert to Kelvins, remember, we will add 273. So 293 Kelvins. Okay. For K, you either have a good memory or you can look back here. So 1.38 times 10 to the negative 23. All right, and this is in joules per Kelvin. All right, and pressure. So that is going to be 101, but it's kilopascal, so make sure to multiply by your thousands. All right, so that's going to be my pressure. And then the volume is going to be 4 times 5 times 6. So 4 times 5 is 20 times 6. That's going to be 120. And that's given in meters times meters times meters, cubic meters. Okay, so I know everything. I'm solving for N. So what I can do is, since I'm solving for N, I can divide on both sides by K times T, right? So if I do that, and please take your time to do the steps so you don't miss something. So if I solve for N, this equation is going to be the pressure times the volume divided by Boltzmann's constant and the temperature. All right, so let's plug that in our calculator. So 101,000 pascals times 120 cubic meters divided by 293, and finally divided by 1.38 times 10 to the negative 23. And you can see that we're dividing by a very small number, so we end up with a very large number. So that's going to be about 3.00, so 2.997. All right, so I'm going to round it up to 3 times 10 to the 27. And that has no units because it's a number of molecules. So I'm going to just write, that's my number of molecules. All right, so you can see it's a huge number, and sometimes, so if you go into chemistry, a lot of the time we're going to actually describe that with a number of moles, so we don't have to carry all these very large numbers of molecules. So we put that in packets we call moles to simplify the notations. Okay, in that case, we would, you may have seen this as PV equals nRT, where another N is given as the number of moles. All right, so this is the equation of state for ideal gas, or the ideal gas law, which is very convenient, as you can see, to relate temperature to other variables here. This is going to be important to later on, because we're going to talk about engines, and we'll see that a lot of them are going to use gases, and we'll see how different processes will be described given, a constant volume or constant temperature, constant pressure, etc. So this is something that is extremely relevant and important, not only in chemistry, but for physics as well. and also for engineering applications, as we'll talk about in an upcoming video. All right, thank you. Stay tuned. Next, we're going to talk about heat and work and the first law of thermodynamics coming up.